taking inferences about two sample means is very similar to taking inferences about just one sample mean. Our criteria are going to be the same. If we're looking for a large sample, if we wish to use the z distribution, we need to know these two things. First is our standard random sample selected from each population. Again, if we don't have that, it's not going to be worth much of anything. And the second one, in order to be sufficiently large and use the z distribution, our sample sizes for n1 and n2 must also both be 30 or more. Now, notation wise, whenever we're dealing with a subscript 1 after our values, be it the mean, the sample size, sigma, that sort of thing, we're dealing with population 1. When we have a 2 after it, then we're dealing with the second population. Otherwise, the notation remains the same. So the confidence intervals for these, again, they're set up as a point estimate plus or minus a critical value times the standard deviation. So we're looking for a large sample confidence interval for the difference of the two means. Well, an estimate for mu1 minus mu2 is going to be x1 bar minus x2 bar, as x bar is an estimate for a population mean mu. Now the expectation of x1 bar minus x2 bar is, as you would expect it to be, mu1 minus mu2. The standard deviation, however, of x1 bar minus x2 bar is this radical here. So instead of sigma over square root of n for just one sample mean, we're going to take the square root of the variance of the first distribution or first sample divided by the sample size for the first, added to the variance of the second sample divided by the sample size of the second. Now, again, typically we don't always have the variance or the population variance or population standard deviation, so you certainly can use the sample variance to substitute for those. So again, confidence interval, point estimator, x1 bar minus x2 bar, plus or minus the critical value. It's z of alpha over 2 because we have sufficiently large values of n. And the standard deviation is this guy right here. Testing for two samples is again very much like what was for one. We're going to see the equal to sign be involved in each of the null hypotheses. In this case, we're looking to see if the mean from the first population equals the mean from the second population. We've got three possibilities for alternative hypothesis. Either the first mean doesn't equal the second mean, the first mean is less than the second mean, or the first mean is greater than the second mean, and you're going to test, you pick one of those depending upon what it is you're trying to find out. So we need a null and alternative hypothesis, a test statistic, and a rejection region to compare it to. The test statistic, again, we get to use a z. The point estimator here is x1 bar minus x2 bar, and we're going to subtract 0 from it. We're going to do that because typically we're more interested in finding out if there is a difference between two population means as opposed to if there's a difference of, say, 20 or a given number. If you actually need to know if they differ by 20 or more or something along those lines, then you can use that value here, but typically it's going to be 0. So we have the value minus the mean, the proposed mean is said to be 0 here, divided by the standard deviation, and this is the same that we saw in the confidence interval. So once we find the test statistic or calculate it, we then compare it to our rejection region or regions. In a two-tailed test, there will be two regions. The lower value or the lower threshold of negative z of alpha over 2. If it's less than that, we reject, or if it's greater than the value of the upper threshold or above of z of alpha over 2, we reject. A left-tailed test, we specifically only reject if it's far left, much lower. So if it's less than the lower critical value or negative z of alpha, remember in this case all of alpha will be available on the left, nothing will be on the right. And the same thing for right-tailed. If our test statistic is larger than the threshold of z of alpha on the right. We can also certainly use the p-value method. Again, this streamlines and makes things far easier for us. If our p-value is less than or equal to alpha, we reject. And again, alpha is our significance level. But if it's greater than alpha, we will fail to reject.